This video tutorial will show an example of a one-way 7-span post-tension slab design using ADAPT PTRC 2019. This might be representative of a parking garage slab, for example, where the supports or transverse beams or girders carrying the one-way slab. So we're going to go ahead and open PTRC 2019. We're going to select the post-tensioned option. This will be performed in US units. The same approach could be applied to a system in MKS or SI units as well. So we'll go ahead now and we're going to first just enter PT input. This will allow us to generate the input data for the model. We're first going to go ahead and select general or specific title. If you want to fill those out on a specific job, those will be reflected in reporting outputs for the program. We'll select one-way slab. Because the slab will be prismatic, meaning it will have the same width and the same reference from the datum or the reference plane in terms of an offset. This will be conventional input. There's another tutorial for two-way slabs that shows how to input segmented geometry. So conventional will be used in this example. We will include transverse beams as supports for the one-way slab, and we'll go ahead and leave off the recommended slab thickness. If we select this, the program will by default recommend that thickness in the span geometry input. So we'll go ahead and select next. We're going to select ACI 31814. We're going to leave the design settings analysis options as set here. One thing to note is we want to make sure we use interactive. This gives the user the ability to interact in the recycling screen, meaning you can change the force profile, etc., without having the program automatically converge on a solution and exit out of the recycler in an automatic fashion. If there are questions about these other selections, you can refer to the documentation found under the Help menu, which gives a definition of each of these different options here for the analysis. Under Design Options, we're going to use all provisions of the code. There is an option to disregard the following provisions. So if we select any of these three or all three, for example, the program will actually ignore that in the processing of the design. So one questionable option here might be the design capacity exceeding cracking moment, which is not technically necessary for an unbonded system using ACI. However, even if we don't disregard this, the program still actually recognizes the fact that we're going to set the tendons to unbonded, and it will not add any additional rebar to meet this criteria. So we'll just use all provisions. Below, under generate moment capacity based on, this just means that for the capacity and demand report that's part of the report generator, block number 32, the program will show capacities which are based on the calculated reinforcement, post-tensioning, and user-defined reinforcement. So whenever you generate design value moment capacities, those should always be greater than the demand. If you use user-entered values, this means that as a user, if you wanted to investigate a slab and you want to see if you have enough capacity, then you can always use this option. The program will then generate capacity based only on user-entered reinforcement, called base reinforcement, or on the post-tensioning, or both, depending on if you have both. So we'll use design values. This represents a new design, for example. The next option allows the user to consider the calculation of minimum reinforcement relative to the transverse beam. For example, if we take just a longitudinal elevation view of this system, we're going to have basically 7 spans that look like this. And if we look at how the program calculates minimum reinforcement at this section cut here, that could either be based on only the depth of the slab, or it could be based on the depth of this full transverse beam, which obviously would lead to more minimum reinforcement. So this option here allows you to consider this full depth for purposes of minimum reinforcement for a one-way slab, which is 0.004 times the area of concrete in tension for a post-tension member subject to, or one-way slab rather, subject to the ACI 318.14 version of the code. We're going to go ahead and leave that off for now. Also, calculation of precompression. The program also can calculate and essentially determine a force necessary to meet precompression. So that precompression can either be relative to only the slab depth or the transverse beam depth. So depending on what you select, if I select this, then you'll likely have a higher force necessary to meet precompression because it's having to calculate, if I take this out of plane for example, it's having to calculate a force based on this full block area versus just the slab area, which might be, just this block here. So you have two options there. We're going to base everything only on the slab depth for this example. We recommend the user make their own interpretation of how the code is read and how that should be interpreted for design. So the option is given here under design options. We'll go to next. I'm going to go ahead and set this up to 7 spans. The outer spans are going to be 30-inch bays. The interior spans are going to be 27.5. So I'll just copy and paste those down. For the width, we're going to just base this on a unit strip. So we're going to say if we have, for example, a plan view, we're going to have beams. These will be the post-tension beams that we'll show also in another tutorial for effective beam design in this program. So we're going to say the span is this way. We have slab spanning this way with 7 spans. And we're going to, because we might have, a unit strip representation, we don't really have to model this full panel. We can model just a unit strip based on whatever arbitrary width you want. Typically this will be 1 meter or 1 foot, 12 inches. We're going to base this on 12 inches. So we'll say that the B dimension here is 12. And the height for this slab we're going to say is 7 inches. If I enter the data in the typical column entry or the typical cell and press enter, that'll push those all into the different spans. And you can modify each span separate as needed. For the reference height, we're going to set the reference height equal to the depth of the member. So if we zoom out here, we can see the datum or the reference line is this line here. If we leave this to 0, that's fine. This allows a user to actually step a member. So if you wanted to offset this span, up, maybe this one down, you could create offsets in the member. However, what happens is if we leave this slab, which is the same elevation along each span, if we leave it as 0, what will happen is the control points for the tendons are going to be based from this datum downward, so they'll all be negative, which is not typically how we may reference them on plans for construction drawings. So I'll set this equal to 7 so that the program will represent everything upward, which will be positive from the slab soffit. So we'll go ahead and press 7, enter. The multiplier, this left and right multiplier, if I go to a plan view, and I'll use these icons at the top to control the visibility of the structure view. I'll go to the plan view, and what this means is that the left multiplier right here, this actually is this side. This is the left side. If I'm standing here looking this way, this is the left side, this is the right side. So we take this B dimension 12, we multiply it by 0.5, and that just pushes a portion of the tributary this way and a portion this way. It's centered, 6 inches on one side, 6 inches on the other. If you wanted to base the design on the full panel width, let's say the full panel width is 30 feet, we could input a 15 value here. And we'll do 15 times 1 foot on one side, 15 times 1 foot on the other side, and now we actually base the design on this full panel. This will be like a full bay in this case. So you can increase this to something greater than 1 if you wanted to. Okay, so we'll go back to the unit strip of 1. We'll go next. The transverse beams now, we're going to define what those transverse beams are. So we're going to say for each support 1 through 8, we're going to have a transverse beam. I'll go ahead and select this and press enter. The height of the transverse beam we're going to say is, let's say this is 21 inches. Okay, this is from the top of the slab down. The D1 and D2 will say it's 24 by 21. So we'll say this is 12 inches and 12 inches. And having done that, you can see the member here. Actually, let me come back to, okay, so I'm just looking at the wrong view here. I'll go back to a side view, and this shows that member depth. You can see there's actually a pin support. By default, when we create a transverse beam, there's a pin support associated with the joint. So those are the transverse beams now. For the support geometry, because we're using point supported transverse beam, we don't really need to fill any of this out. If you did have a wall below or a column, for example, typically a column might be more associated with a two-way slab versus like a wall, which would be a continuous support, which would then, you know, fall into the category maybe behaviorally of a one-way slab. If you have a column support, typically you would have two-way bending near the column. So we'll leave the lower and both walls options set to off. We're using the transverse beam option. This left and right edge, this is applicable only to two-way slabs. That's defined in the two-way slab tutorial. For support width, we're going to take a look at some of these options here. By default, the support width is set to 0, which means that the program doesn't have a width that it can dictate where you're going to cut face of support moments and shears and design values at. As the user, you can choose to select support width here. That will automatically define the support width as the dimension of the transverse beam. If you wanted to try to override this, notice it locks you out unless you deselect, and now you can actually override to a different value. So this tells the program where to cut face of moment and face of shear values off for the design. We'll just use the transverse beam width. You can also modify here the support fixity at the joint near the slab or beam, if this was a beam design, or at the far end. That's controlled here. Notice these are all inactive because by default we have a transverse beam which always creates a pin support at that location. We'll now go ahead and load the slab. We're going to turn skip live loading on. Skip factor means that whenever the skip live load is applied, maybe it's applied in this bay and in this bay and in this bay for the first of 6 patterns, the program uses this skip factor to the application of those different live loads. So define the skip off or on, define the skip factor for the live load. You can include self-weight automatically, which we're going to do. The program will calculate the self-weight of the members automatically for the analysis. I can either input the span number here, so maybe I want a live load and a superimposed dead load in each span, or I can select all, and that will fill out all spans the same. So we'll just say all here, all there, and this is going to be a live load. I can select the identifier for the load type. This is going to be, for example, a line load. Maybe it's a partial uniform, concentrated. I'm using the second character in these descriptors in this input to change the different parameters that define the load type. So here I'll just use uniform in both. We're going to say that the dead load is 15 PSF and the live load we're going to say is 50 PSF. This is all written in terms of kips per square foot, hence the entry for 0.015 and 0.05. So once I select next, you can see if I come back to that, this actually gets extrapolated out to each span. If you wanted to add other load to all spans, I could just enter a new character here for all, and so on. Other classifications of load are X load, which is just kind of a wild card load, if you will. And if you turn off the self-weight inclusion, this will now allow you to classify load as self-weight also within this dialog. Okay, the strength of the concrete we're going to say is 5,000. If I press tab, the modulus does not change. You need to press enter, or you can manually override this. If I press enter, the modulus changes. The creep coefficient will be 2, and the concrete strength at stressing is going to be 3,500. This is typically about 0.7 to 0.75 F prime C at 28 days. We'll go to next, and here we're going to determine our material for the reinforcement, both longitudinal and shear. We're going to leave the yield and the modulus alone. I'll go ahead and change the slab sizing to 5s and number 6 is on the bottom. For shear reinforcement for the slab, typically we wouldn't have any, but we'll just say this is number 3 bars with 2 legs for each 12 inches of unit width of the slab. For post-tensioning, we're using unbonded half-inch diameter low-lax cables. Ultimate FPU is 270 KSI, and the effective stress we're assuming is 175 KSI. This value, if we multiply the effective stress here by the area here, we're going to assume basically an effective force of 26.7 kips per cable. So that's our force assumption when the program generates a required force for the unit strip. Now we could use the calculated force method, in which this number doesn't really mean anything. The calculated force method allows the program to actually calculate the loss along the length of the cable. So we'll show that entry here in a moment. If you wanted to add any minimum reinforcement or base reinforcement to the members, you could select yes, and we could then fill out this table based on the reinforcement. Just as an example, we're not going to use this, but if I say I want a bar in the 2 end bays at the bottom, I'm going to say, okay, I want an isolated bar. The first end location is going to be in span 1. The second end location will actually be over in span 7. It will start at 10% the span length in both spans. This is relative to the span start and end point. The second end location we're going to say will be in span 1. This will be in span 7. And we'll say this is 0.9 and 0.9. Bar size, I'll use number 5s. We'll use 4 bars. Actually, let's use 2 bars for 12 inches. And this is going to be a bottom bar. Cover we'll say is 0.75 inches. This is cover to the longitudinal bar. Okay, and by doing that, if I go back to the top view, the program's added bars in this span, 10% from the left side, 10% from the right side. And if I go back to the extents here, you can see the bars over here also. So this is just a way to add known reinforcement in the spans as needed, top or bottom. For this example, we'll go ahead and select no. We're not going to actually use the base rebar. We're going to allow the program to just calculate the reinforcement for us. For the allowable stress criteria, we have top and bottom tension stress allowables for initial, sustain, and total. For a one-way slab, they're treated similar to beams. For the ACI code, we can have anywhere from 7.5 up to beyond 12 for the allowable stress. We're actually going to design these to 6 for sustained load and 7.5 for total. And so you can dictate, what's my allowable stress under different loading conditions. This might be a little bit conservative unless we really want a watertight, if this was a parking deck, watertight limit cracking, no cracking whatsoever, then we might actually back this off to even below 6. We might have 2 or 3 square root of F prime C. So there can be any number of different inputs you make here for the allowable stresses. The compression stresses here are just based on the code. We're going to target a pre-compression of 125 to 300, and we're going to target a percentage of dead load to balance between 50 and 100%. Okay, the design or the calculation options I mentioned earlier can be either force method, effective force method, where we base the tendon force on the average force, basically constant along the length of the tendon, which was 26.7 kips, or you could have the program calculate the force for you. This will be variable force or calculated force method, where we calculate friction loss and also, if you want, long-term loss based on these parameters here. So This method is available in the program. Even if I select calculated force method, the program in the recycler gives you the option to toggle between force or calculated force. So I'll show that in this example. We'll leave this set to these defaults. This here dictates the profile of the tendon in each span. So spans 1 through 7, we're saying that we're going to use a reverse parabolic shape where we have an inflection point at x1, x3, and x2. If you want a simple parabola, then you basically would set reverse parabola shape and set the x1 values to 0. That would give you the simple parabola, or you could use a shape 2, a partial parabola, and do the same thing. We'll just leave the defaults alone here. This dictates the shapes for tendon A, tendon B, and tendon C. So tendon A will always be passing from span 1 all the way to span 7. It goes through the entire set of spans in the model. Tendon B and C can be anchored at any location as long as it's within one span. So if I needed an add tendon here, I might add a tendon there, and then maybe over here on span 7 I might add a tendon there where we might have additional force required because it's a longer span and it's at the end bay location. So these are mainly used for add tendon placement. We default this back span, that might be a cantilever back, cantilever down shape behind this support. When we have add tendons, we default that to 0.2 times the span length times 27.5. That's dictated here. And you can modify it even if you leave this to 0.2. When we get into the recycler where we're making changes to the tendons, we can go and we can stretch this way, we can stretch it this way, as long as you don't go past this second support for the tendon. You can move the tail of the tendon even though this is set to 0.2. You also can determine how the tendon anchors. If this is our slab, let's say we have a column, and I'll just blow this up, and we have an add tendon that is down here and it comes over the support. The question is, where does this thing anchor? Here. Does it anchor at the mid depth so we don't induce any moment into the slab? That's an option. That's the default option here and here. Or does it just follow the shape function for this cable, for this reverse parabolic shape? If it follows a shape function for this, then you're likely going to have the centroid here and this eccentricity, and you're going to crank a moment into the slab at that location. So typically we're going to anchor at the CG of the slab. We'll use the defaults in this case. Okay, the cover, the criteria, we have one set to the top fiber and the bottom fiber and interior spans. Exterior for fire rating, we may need this to be a little more. This is 1.75. We'll assume this is an unrestrained condition where that may dictate needing more cover, again, for the exterior spans. And then we have our bar covers here for reinforcement. The way the program generates reinforcement can either be based on these simplified settings, which are just cutoff lengths for bars over support. So when the program adds rebar at support, it's going to extend it 0.17 to one side, 0.17 to the other, and then in the span it will be 0.3 to this side, 0.33 to this side. And it will also apply these extensions to strength reinforcement. This might be for minimum reinforcement. Strength reinforcement would be dictated on the moment diagram. So if I have a moment diagram that looks like this, then we determine, okay, where's our cutoff inflection points? There's 0 moment here and here. The program might say, okay, take half of the demand. If this AS, I'll call it ASM, AS max. If I go down and cut that in half, maybe this location here, this is called, let's say, AS2. The program might require bars to run from 0 to 0 plus the extension that meet AS2 plus another 2 bars that extend, past that AS2 mark. And the program's algorithm usually will cut bars into 2 different segments like that to try to economize the design rather than just running the requirement for AS max beyond point of 0 moment. That's what this cutoff is here. You can also dictate and customize the curtailment of rebar in the next window. So this allows the user to set up how the bars should be curtailed and customized. If you use ACI 318, then that kind of follows the ACI code requirements for top and bottom bars depending on location of the bar. We have entries for both long and short bars, and then the percentage of the bar or the total area of still that gets allocated to each bar type, long or short. You can also go to adapt. If you use adapt, this actually fills out this table based on these inputs here. So this input here should actually be the same as this if you use curtailment. You can turn curtailment completely off. You don't have to use it, and the program will just default to this output here, which is what we'll use in this case. So you can set curtailment for top and for bottom bars. It is an option. For this simplified example, we're going to just allow the program to base it on the default options in the previous screen. The last input will be the load combination. So we have strength combinations, which include the secondary moment of the post-tensioning. These are gravity oriented, and we're going to also include two service combos for sustained load. Notice there's a 0.3 factor to live load and X load. We have no X load in this model, so that really is just 0. And then for total load, we consider all load applied unfactored. The initial combination includes only the self-weight of the system plus 1.15. The 15% is the increase in the PT force because at initial condition we're just simply adding back in the long-term loss on the cable using the 15% estimate. You can also, if you needed to include joint moments at the joints, if this was a frame, for example, a moment frame, and you were designing it also for lateral moments. This really applies more to beams, I think, but we could include lateral joint moments here and also additional combinations, including those lateral moments. So the moments are input in this table. The combinations are then dictated here. Okay, we're going to leave lateral off for this example. I'll go ahead and select OK, and I'm going to save the model. Okay, now that the model is saved, we're going to execute the model. So the first thing the program is going to do is determine what post-tensioning we need for this 7-span one-way slab system. We'll go ahead and run that. This may take a few seconds to run. You'll notice it's kind of working in the task bar below. Once it's done, it will basically show the recycler. This is called the PT recycling window. We call it informally the recycler. So in the recycler, we have a lot of information here relative to the design. First, we're using effective force method by default. We've set the criteria to meet min and max P over A, that's this option, balance loading min and max, and then whether or not we're meeting the stresses sustained and total and initial. The table at the bottom shows the current tendon, which is selected here. This is tendon A, and then all tendons, which would be the sum of A, B, and C. Well, we have not yet set anything to tendon B and C. We're only using tendon A by default, so these tables really should match right now, this one and this one. Once I add tendons B and C, then this would be the sum total of all 3 tendons that are used in the design. So the current proposed design by the program shows that the force for a 12-inch wide strip is 30.8 kips, which means that the precompression is a little bit higher than what we set. We set an allowable max of 300 psi. So we still may be able to live with this, but because we set it in the input to 300, it's actually flagging it as no good. That does not necessarily mean it does not meet code. It just means that it does not meet a constraint that we added inside of the allowable precompression in the input of the program for this particular model. So the minimum precompression is fine. That's above 125. The balance loading is above 50 and below 100. That's all okay. And then the stresses, tension and compression, say okay. Now if I go to tab 4, I can see for total, my allowable for total was 7.5. The end bays are pushing right at 7.5. As you get interior wise, those interior bays actually have no tension at the bottom fiber. And then we can also look at sustained. The sustain we set to 6 square root of F prime C, and that's a 70% decrease in the live load, so we're well within the range on sustain. So what's really controlling the design is the force necessary to meet the total allowable tensile stress. That's indicated here, 7.5. If I go over here to tab 3, required PT force, you can see right away, center end bay based on tensile stress, this is the force necessary to meet that. That's the controlling force, 30.8. The force to meet P over A minimum is really 10.5, so that's quite low. And then the program just bases everything off of that max number, 30.8. So we kind of look at this and we say, well, we can maybe economize this design. We have a requirement in all of our interior bays of only 16 kips of force. It's only the end bays where we require 31. So what I'm going to do is I'm going to change this to, actually it's 18 right there. I'm going to actually change this to 20. So tendon A is now 20 kips. But I want to change the end bays to the balance, which is 31 minus 20. We'll just say 12. So I'll go to this tendon selection option, and I want to make sure my tendon B and C add tendons are in the right position. I could select control and move this, slide it if needed, or I can make the changes in this table. Here, this is 20% into span 2, so it's 1.2. If I wanted it 50%, I would say 1.5, and that updates that. So let's go back to 1.2. Okay, so I'm going to introduce add tendons, and I'll come back into tab 1, and I'll go to tendon B, and I'll say, well, for this tendon, this is going to be 12 kips for tendon B. This is the profile of the tendon. It should typically match tendon A in this case. For tendon C, it's on the opposite end, so I'll do 12 kips there. Now my total is shown here. Notice this total 32, 20, 20, 20, 20, 32 is the sum of all tendons A, B, and C. Once I make a change in the recycler, I need to recycle the design. And this will run through it again. And now I have a design which is, it's more tuned in, it's more economized, if you will. So we have a force, a total force of 32. Notice only the end bays now exceed P over A max. And we'll say, okay, we're going to live with that overage in max P over A. The other bays are well within the 125 to 300 range, and our total balance loading is okay also. Okay, if we go to graphs, this will show us the different inputs here. So if I maximize this graph, I'll right click, you can see this red represents tendon A, the blue represents B, this blue represents C. So we have A, we have B, and we have C. Okay, we'll go ahead and escape out of there. And we can also look at stress graphs, for example. If I want to look at the total bottom fiber stress, we can see the green is tension. So right here we're getting max tension. That was why we had to add the tendons here and here. We're getting this high moment demand on these end spans. This lower graph shows us the force profile. The required force is shown by each of these lines at each data point. So we can see we have a much higher required force near spans 1 and 7 versus the interior span. So our actual force, 32 down to 20, does this kind of step curve here. That's the actual force required. Okay, so this will be a satisfactory design again if we're willing to justify the fact that the max P over A is greater than 300. If I don't want this no good to show up, I would just go back into the input and set my max to 400, which is a that could be an applicable modification made to the design. Again, max P over A is not dictated by code. It's more a function of economy for the design and constructability, whether you can actually fit enough tendons within a 12-inch space where they anchor for this particular design. So we'll say that this is a workable design. Now, if I switch from the effective force method And remember I said earlier that this is kind of the average force. This is a flat line. So we're assuming an average force along the length. There is a step, but even where it steps to a higher value, it's still the average force in that span. I'll go ahead and close that again. I'm going to go to tendon selection method. And if I go to tendon selection method, now the program is going to calculate the force for us. So we can see that the average force for the tendon selection method is around 27.2 kips for tendon A, 27 for B and C. And we need to specify the number of strands for each one of these cables. We're going to say we're going to use tendon A first only, and we'll say there's 2 strands with an average force of 27. I'll just go ahead and recycle. If I go back to this tab, you'll notice that the PT force varies right here. The tendon shows this arrow is a live end and a live end. That's why you get symmetry with the force, 52.7, 55 on either side, and it's symmetric about the center of the tendon. We say, well, we're not going to have live. We want to have live dead. So I'll use shift, change this to a dead end, and recycle. Okay, and now what we see is this type of profile. So this is a varying profile. We're losing force as we move from live end over to dead end. This is live to dead, and this loses force. The average of this curve is roughly 27.2 kips. So it's actually more than the assumed effective force of 26.7. And that might be why this now fails. The stress for initial and tension exceeds 3. If I go back to tab 4 and select initial, this is up at 5, 6, and the code allows you to add reinforcement for overstress under the initial condition. So the program will actually add that reinforcement. So even though this is no good, the program adds reinforcement for that one condition per allowance by the code. Balanced dead load is also no good. You can see we have more dead load balancing than we want for this case. And that again might be because we actually have more force than what we really need. Originally we needed 31 kips. Well, now I selected 2 tendons with an average force here. It's actually back down once it calculated to 24.6. I have a force of roughly 50 kips. I could set this to 1 and recycle, but nothing is going to work in this case in those exterior bays. Now we only have 27.5 kips in the exterior bay, and we needed roughly 32 kips. So we can come back and say, okay, use 1 tendon A, and then we'll use 1 tendon B and C in those positions. And we'll recycle again. And we're kind of back to where we were initially. We have some overbalancing. Maximum is no good in this end bay. It's 105%. Again, why is it more there than the end bay? Because that's the live end. This is the dead end. We lose force going from live to dead. This would also be most likely a workable design as well. We have a little bit of overbalancing. I can adjust this cable profile. Maybe I bump it up to 2 and recycle. This is down to 101. Everything else is working. I can adjust that maybe a little bit higher. Let's move it up another 1/2 inch. And now we're less than 100. So this is also an option. If we have overbalancing, we can try and adjust the cable profile. After we've designed the post-tensioning cables in this interface for PT Recycler, we're going to exit. And now the program can calculate reinforcement and deflections. Once it's done that, it will go back into the program shell, as we call it. And the shell allows the user then to look at results. The most commonly used result in the program is found here, this summary icon, this yellow icon. So we'll go here to the summary. Graphically, for any load combination, we can show shear, moment diagrams, etc. for the combination. We can show reinforcement demand for the combination. We can show stress diagrams for the combination. This would not produce for strength because we don't check stresses for strength. Maybe I want to look at service stress. So graphically we can show combination results. The real nice report here is really the summary. I'll go back to envelope and I'll look at the summary report. This is just a report that can be produced as a printout or PDF, and it shows the geometry, the reinforcement top and bottom, and the way it's allocated within the span. The number of layers just means that the rebar can be placed in one layer, not two or three or four. This is saying it will fit within one layer. The profile of the cables, and then the forces. This is the force of tendon A, B, and tendon C over here, and the CGs of those different cables. It's also showing the elongation. Because we did calculated force method, it's showing that at the live end here we have an elongation of, for example, 14.63 for tendon A, 2.83 for tendon B, and then 2.83 for C. Additionally, we can look at some graphical results for required and provided rebar along each span, top and bottom locations. There are no shear requirements for this one-way slab. This is basically 0. And then we get deflection diagrams in the second page here on the bottom. So these deflections, we want to check and make sure those meet the requirements. If you need additional information on how the calculation of deflections work, you can look at the user manual for ADAPT. There's a deflections section, and that shows an example on how the deflections are calculated and how the creep factor is taken into consideration for the sustained loads, self-weight, dead load, PT, and also a portion of the live load under sustained condition. So this is builder sum. I'll close builder sum. If we use this option here, this is what we call the shell results, and these just show kind of the raw results for bending, shear, deflections, stresses, and so on. So the difference between this and builder sum is these are raw results which you can then combine into combinations using these selections of load cases. They're not necessarily each individual combination plus the envelope result. Lastly, if we go to the report setup, we can produce a tabular report of selected options here. So if I go to the compact report, for example, and I want to look at the total compact report, the compact report versus the detailed report, compact would mean that the program produces results for, if these are my spans, at left, center, right of each span. The detailed report shows results at every 20th point on each span. So this gives you much more detail in terms of the different output for shear, moment, deflection, etc. for the system. And then you have a concise report. The concise report just predefines several options for the report format, geometry, applied loads, design moment. This might be the most common report if you just want very basic results. Compact report is actually recommended for a more thorough report, but not doesn't take a lot of time to produce, and it's gives you most of the information you need for a submittal. So under tabular reports, if I go ahead and just create that report, the program will allow me to generate this as a Word document in an RTF format. Okay, and this is the format. You can see it's just a tabular report with different blocks of information relative to the design. So this report, along with the builder sum summary, is a good compilation for each design and a submittal for a design. You can also save a report. Maybe you only want to save, for example, deflections. So if I say I want to go to compact deflections and also maybe detailed deflections, then I can select both of those. I can go ahead and save this selection, deflection report, select OK, and that should be then saved here under the selection option for user-defined reports. If you have any questions about this tutorial, please contact us at support@adaptsoft.com. And there are two other accompanying tutorials, which are the beam tutorial, which is a post-tension beam, and also the two-way slab tutorial. Both of those will show information that may not be relevant to one-way slabs, but may be only applicable to those two design types. We recommend you check those out also on youtube.com/Slab